will look through those again. Okay, so now we are going to, if you have the table that I showed you for the reduction potentials, you're really going to need that today. I'm going to try and do my best. Usually, again, if we were in class, I would give you an actual physical table, and then you would have those in front of you while we're doing this, because you're really going to need that table today. So we're going to talk about mixtures of ions. So like, what if you have multiple possibilities for oxidations or multiple possibilities for reductions? How do you know which one is which, right? How do you know which one will oxidize? How do you know which one will reduce? So the rules of which one will oxidize and which one will reduce is the same as we've done before, whereas the one that's going to reduce is going to be the one that's closer to the top. So the one that's more positive or least negative will be the one that reduces, right? For the oxidation, the one that is more negative or least positive, again, however your brain works on that one is going to be the one that oxidizes. So if you're looking at the table, I have a table here. If it's closer on the top, that one's going to be the one. If it's closer to the top of your table, that's going to be the one that reduces. If it's closer to the bottom, that's going to be the one that oxidizes. So for example, if you have an anion, like, I don't know, Cl minus, there's no such thing as Cl2 minus, right? Chlorine only has that, it's only, well, let's not use chlorine. Let's use fluorine because chlorine can change. Let's use fluorine. Like fluorine only has an oxidation state of -1. It can't go to -2, so it can't gain. So if you have an anion, it's probably going to oxidize. If you have a cation, it's probably going to reduce. And again, because the cations will gain electrons, right? So like Ca2 plus will gain electrons, so therefore it's reduced. So cations are typically reduced, and they're going to be higher on the table. Anions are typically oxidized. Now, again, the reason I say this table is really important because you're going to see we're going to be looking at a lot of oxidation. We're going to be looking at a lot of reduction potentials, but it can get tricky in your brain because when it oxidizes, right, the reactions flip. So I'm going to try and do my best to make sure I am like very clearly telling you the differences on these. So just so you know, in general, this is typically the oxidation reduction for water. Water's on here a few times, and you're going to see we're going to use this. This one is typically the reduction reaction for water. Now, and we're going to keep using those. So again, when you have more than one cation present, right? The cation that's the easiest to reduce, or closer to the top, or least negative, or most positive, higher on the table, that's going to be the one that is reduced. Okay, so now let's look. So we have a half reaction where we have aluminum, magnesium, and bromine, right? So we have all of those ions flying through here, right? So first of all, we know that bromine will have to oxidize, right? Because bromine, right, Br minus, it can't gain any more electrons. Its oxidation state is -1, -1. Oops, I don't want to give you all the answers. So we know that bromine has to oxidize, right? It can't gain electron. It can only lose, right? So our bromine is our oxidation reaction. We know this, and I think I have this on here to help you. No, I only have the whole answer. So the anions, just so you remember, I'll write it on here. Anion, this one is usually oxidized, right? And our cations are usually reduced. And again, I'm going to keep explaining this over and over again, why the anions are oxidized, why the cations reduced. Remember that our anion, in this case, our bromine, has an oxidation state of -1. It can't be -2, right? It is -1. There's no other choices. So it can only lose, right? Our cations, our aluminum and our magnesium, they need to gain electrons, right? So here are, and I have, oh good, I put this on here for you. So if you're looking at your table, I just took the reduction potentials from the table and put them on here. And so you can see magnesium is -2 and aluminum is -1. right? So whichever one is closer to the top of the table, and remember, I'm just gonna go back to the table, just so maybe this can help you. So if it's closer to the top, look at, see, here's like 2 down to like 0.4. So closer to the top means more positive, right? If I look over down here, right? If I go closer to the top, less negative. So that's why I say like more positive, less negative, closer to the top. And that's why it's helpful to have the table in front of you. And I'm going to keep saying it all 3 ways, just in case to help you. Okay, so whoever's closer to the top or more positive or least negative will be the easiest to occur, right? That will be the most likely reduction. And since aluminum is closer to the top or less negative, more positive, right? That will be the one that will be reduced. So bromine will be oxidized and aluminum will be reduced. So if we look at this, I think I only have it the whole thing, right? So here's our 2 options for our reductions, right? So remember, our cations are going to be reduced, our anions are going to be oxidized, right? So if you're having trouble remembering it, just remember that piece, because that's going to help you. Cations are going to be +3, +2. Cations are reduced, anions are oxidized. Okay, so these are our 2 choices. Now, how do we know which one it is? We look at the table and we find their reduction potentials. Because aluminum is closer to the top or less negative or more positive, that means it will be the easiest to reduce, so therefore it will occur. So if we want to know what's happening at our anode and our cathode in this case, remember, reduction always red cat. Reduction always happens at the cathode, right? So our reduction will be at our cathode and our oxidation will be at our anode. Right? So it's the same principle that we've been doing, right? So before we just had 2, and whichever one was higher on the table, that one was reduced, and whichever one was lower on the table, it's oxidized. It's the same thing here. It's just, first of all, you need to figure out which 2 could oxidize and then which 2 could reduce, and then whoever's higher reduces, whoever's lower oxidizes. Okay. Oh, see, I knew I had it written here. There it is. Anion, oxidized, cation, reduced. Okay, so let's look at this one. So in this case, and again, magnesium +2, chlorine -1, +2, -1. So you can see here we have 3 choices. So we have magnesium, which is the cation. And remember, I have it on here, cations are reduced. So we know that magnesium is going to be reduced. And remember, the reason that cations are reduced is because you can't lose any more electrons. Like there's no higher oxidation state. Magnesium it's going to gain, right? So it's going to reduce. Okay, so that's going to be our reduction. Our anions are going to be oxidized. So either chlorine or bromine. All right, so now we look, chlorine and bromine. Okay, so here's chlorine. And I literally took this straight from your table this time. And there's bromine. Okay, so we have 1.09 or 1.36. And remember, these are anions. So anions are oxidized. Okay, so when we look at this, let's see here. What's our choice? Our choice is either bromine or chlorine. Okay, which one do you think it is? You have 2 choices. Type it in the chat. Do you think it's going to be bromine or chlorine? Who's going to oxidize? Remember, the anion that is the easiest to oxidize is closer to the bottom. So our anion, I'm just going to say anion oxidized. Oops, that's supposed to be an eraser. Anion is going to be oxidized, which means closer to the bottom or less negative, which also means more positive, which also means closer to the bottom. There's my shorthand for you.
If it's closer to the bottom, wouldn't it be more negative and less positive? Or am I not thinking that?
Less. Yeah, did I write that backwards? Let me go. Let me look at my thing really quick. Hold on. Just want to make sure that I have it right. Where's our chlorine and our bromine? I think I copied these right, just to make sure I did this right. Chlorine on these ones. Yeah, so closer to the bottom, more negative, less positive. More negative, less positive. Let me see, oh, I erased it already. More negative, less positive, right? Let's just write that again so I have that all correctly on here. So oxidized is going to be our anion, which is going to be more negative, which is going to be closer to the bottom. Yeah, I think I wrote it backwards in my brain, which is going to be, or I'll just say less positive. And again, whichever way it works in your brain, it's hard for me to say all three ways because I have the chart memorized in my head. So I know that the positives are up here and the negatives are down here. So in my brain, I just say top or bottom. But I want to make sure that in case your brain doesn't work that way, that I'm saying it which way your brain does work. So hopefully I'm not confusing you by always using all three. But in my brain, I just say closer to top, closer to the bottom. Okay. So again, if we use my brain way, this one is closer to the bottom, which is also going to be more negative or less positive, right? So this one's going to be more likely to oxidize, right? So it's going to be easier for it to lose electrons because it's more negative. Because remember, electrons are going to be repelled by something more negative. So this is going to be our oxidation. Chlorine-ware reduction. And so when we do this, the question says predict the half reaction occurring at the anode and the cathode. Now remember, reduction always happens at the cathode, right? So our Mg, that's going to be our cathode. And our Br, this will be our anode. Right? And then you can just combine those in a half reaction. Do I have them? Oh, I just have the whole thing again. Okay, so again, here's our whole thing. We had to choose these two were our possible oxidations. Our reduction only had one choice here. And so our oxidation, again, now you can see here, I wrote these as oxidations. This becomes tricky because remember, a lot of times people get confused because I say like this is going to oxidize, but remember when it oxidizes, these two are going to flip. But I also want to remind you, all of these things I'm saying right here are all talking about reduction potentials. Right? They're all talking about reduction potentials. So even though we're saying that either of these could oxidize, they're not going in that direction, right? They're going to flip. And remember, when you flip them, these become negative. But when we're using these words I'm using here, I am specifically talking about reduction potentials. So if I asked you what is the potential for this reaction, you can't flip these yet. You can flip them after you've decided who's going to oxidize and reduce, then you can flip them. This is why in my brain, I use top and bottom, right? Because then I don't have to worry about negative and positive, right? Because look what happens here. So I have this as a plus and a plus one. If we wanted to figure out what the total voltage for the cell, if I asked you for the E cell, well, then you're going to flip these. And see, I just flipped them. But remember, you can't use negative and positive now because I just flipped them both. So you see what I did? I actually wrote them as oxidations here. So I just want to make sure that you understand when I write it as an oxidation, you can't use the more positive or more negative. You can use closer to the top, closer to the bottom, right? So if you look at these, this one is closer to the bottom. That's going to be our oxidation because it's closer to the bottom. So it's really hard when we flip them because in your brain, you're like, wait, what? So pick a way you like to do it and then do it that way. I might just keep using closer to the top and closer to the bottom because I think that makes it clearer. Okay, so now to throw another wrench in it, oxygen has multiple places multiple places to oxidize and reduce, right? So here's the reduction of water to H2. So this one right here, if you look at your table, it's 0.83. But usually when we talk about water, did I say oxygen here? I'm not water. We're in water, it's not 0.83. In water at a pH of 7, it's negative 0.41, right? This is at standard condition. This is like, right, 1 molar, but water's not 1 molar, right? Water's 10 to the negative 7th molar. So this is 10 to the negative 7th molar, which is what it is in water. So the reduction is different in water. Now, same thing with the oxidation. And so I wrote your oxidation in 2 different ways because I want you to understand the difference. So here is it written on the table. Remember, it's an oxidation, but we write everything as a reduction potential because that's our universal way of writing things. So these oxidation reactions, again, are written as reduction potentials, but no, this is what they actually do, right? This is written as an oxidation here. So again, the oxidation of water in standard conditions, again, at 1 molar is 1.23, but water isn't 1 molar, right? It's 10 to the negative 7. So at 10 to the negative 7th molar is plus 0.82. But again, if you're adding your reduction potentials, you need to remember to flip them, right? But I'm going to write them mostly as reduction potentials today, just because I want you to keep it straight into your brain when we do this. Okay, so half reactions that lead to the least negative E cell will occur unless we have overvoltage. So we started talking about last week about electrolysis, right? And electrolysis is different than voltaic cells. So a voltaic cells, right, it occurs spontaneously. But in electrolysis, what we're gonna do is we're gonna force it to go backwards. So we're gonna add energy to force the electrons to go the other way. And we have to add a little bit more than we calculate. And that's what I mean by overvoltage. So let's say like your E cell was, I don't know, negative, it was like negative 1.4. That's not a 4 volts. That's not a V. In order to get this to happen, you would have to add more than 1.4 volts. You would have to add 1.41 volts because at 1.4, you would hit an equilibrium. So nothing would happen. So overvoltage means more than. So if your E cell was negative 1.8, you would have to add more than 1.8 to make it go backwards. Okay, and we're going to look at some of these. Okay, so now, remember, anion oxidize, cation reduce. So the reduction with the more positive, higher on the table, right, is closer to the top, will be easiest to reduce. The oxidation, closer to the bottom, easier to oxidize. So that's how I think of it in my brain. So let's say here's our choices. So here's the reduction for water, here's the oxidation for water, and then here's sodium and here's iodine. So what we have here is sodium iodide in water. So we've got Na+, we've got I-, and we've got water. Water could be oxidized, water could be reduced, just depends. So I found the reduction potentials and I wrote these all as reductions in this case. Okay, so who's going to be reduced? Cations are going to be reduced, right? So our choice here for our reduction is, here's the water reduction. So this could be reduced, right? Or sodium could be reduced. One of these two. So when we look at these numbers, we see negative 0.41 or positive negative 2.71. Okay. 50-50 way. Okay. So when you're looking at this, so someone had a good question. Can you tell this without using the table? Yeah, you just need to remember, right? The top of the table is positive. So the more positive it is, so if you have the table goes from positive to negative. Positive, reduction. Negative, oxidation. Closer to the top, more likely to be reduced. Closer to the bottom, more likely to be oxidized. So if we have these two, we have negative 0.41 and 2.71. Which one do you think is going to be reduced? Water or Na? You have a 50-50 shot at this one. Your choice is either water or Na. Which one do you think it's going to be? Seeing a few of these. Remember, the one that's more positive is going to be reduced, right? So this one will be our answer. This one's going to be reduced, right? No, that one is not more positive. Water is more positive. Okay, so remember, more positive. So I'm trying to think of how, because a bunch of you just said Na here. Whichever one is more positive is going to be reduced. Whichever one is more negative is going to be oxidized. Negative 0.41 is more positive than negative 0.271, right? So remember, reduction means it's going to gain electrons. So electrons are going to go towards it. In order for it to go towards it, it wants it to be more positive because electrons are negatively charged, right? So they won't want to necessarily, in this case, they have no choice, but they're going to go towards the 0.41. So in this case, our reduction, negative 0.41 is more positive than negative 0.21. Okay, so I'm going to go to this next part to help you with this. Here's our picture. Let's do it with our picture. So we've decided, here's our possible oxidations. 0.54 or 0.82. Okay, which one do you think will be oxidized? It's either going to be water or I2. Which one's going to be oxidized? Yeah, type it in the chat. Yeah, it's going to be I2 because I2 is closer to the bottom, or you could say that it's more negative, so it's easier for it to extract electrons, so therefore it's going to be oxidized. Closer to the bottom, easier to oxidize. So this is going to be oxidized. So I is going to be oxidized. So remember, when it's oxidized, we flip it, but we need to decide that this one is going to be oxidized before we flip it, right? So I just flipped it, but we already decided that one's going to be oxidized, right? It changes. So for our reduction, again, we have either negative 2.71 or negative 0.41. So for our reduction, the half reaction with the more positive E is the easiest one to accept the electron. So therefore, water is reduced at the cathode, right? So this one's more positive, and so this is going to be our reduced. Right? So now, if we wanted to know what our E cell was here, we would add this one and this one, right? And you can see, in this case, we're going to have to add a voltage to make this occur, right? And we talked about that with our last lecture for our electrolysis. Okay, so our overall reaction would be, here's our 2I, right? Here's our 2 waters. And then here's our I2. Here's our H2. And here's our OH. And you can see our electrons are indeed going to fall out. And so this is our overall balanced chemical reaction. Okay. I'm going to have you try one now. Are you ready? Okay, I gave you the voltages. So I want you to predict the half reaction occurring here. And so this is lithium iodide in water. And so I gave you the oxidation and reductions. Well, that was really nice of me. So now you just need to pick out which one's going to be at the anode and which one's going to be at the cathode. Okay, so I want you to try that right now. I just want to know which one's at the anode, which one's at the cathode. So try this, and then we'll go over it in just a minute. Okay, so for oxidation, we have two choices. And remember, these are our oxidation choices here that I gave you, because this is the oxidation reaction for water. Anions are oxidized, right? So that's why we chose these two. So remember, for oxidation, the one that's closer to the bottom, or the one that is least positive or more negative, is going to be the one that is oxidized. And so we have 0.54 or 1.23, right? Least positive or more negative, that's the top one, right? So it's going to be our iodine that's going to be oxidized. So remember, when we oxidize this, we're going to flip this, right? And then we'll flip the sign. But first we decide it's oxidized. For our reduction, it's the opposite. So whoever's higher on the table, or more positive or least negative. And the reason I keep saying both of those words, because here's our choices. It's either negative 3.04 or negative 0.83. Well, the one that is least negative, right? The one that's least negative or more positive is this one. And so therefore, water is going to be reduced and iodine is going to be oxidized. So if we want to know which one's at our cathode, reduction, always red cat. Reduction is always at the cathode. So this will be our cathode. And oxidation, this will be our anode. But now if we wanted to know what the potential was, we would add this with this. And again, you can see, what did I do right here? I flipped. If I flip this reaction to make it look like an oxidation, so then we flip it. Okay, one more. Okay. So we're gonna try one more. Okay, try this one and then we'll go over it in just a second. Okay, so this time I didn't help, right? So we need to decide which ones are going to be the oxidations, which one are going to be reductions, right? So we have four choices. So I tell you that I just tell people to memorize the water oxidation reaction because it'll make your life easier. And then just memorize the water reduction reaction. It'll make your life easier. So that means we need to choose with the bromine. Will the bromine be oxidized or reduced? And will the sodium be oxidized or reduced? So remember, the anions are always going to be oxidized and the cations are always going to be reduced in this case, right? So our oxidation, anion, is our oxidation. So this is a possible oxidation. No, don't show you the answers. This is a possible oxidation. And remember, that's because it's going to flip, because this is -1 + 1. So it's going to go the other way. And our cation is going to be reduced. Another way you can think of it is it goes in the order here, right? If that's a -1, that's going to be a reactant. That's a +1, it's going to be a reactant, right? So if this is an oxidation, right, this reaction is going to flip. it's got to be an oxidation, right? It's in whatever order you have here. That's a +1, so it's got to be a reactant. That's a -1, it's got to be a reactant. So therefore, this is likely going to be an oxidation. This is likely going to be a reduction written as is. Oxidation, it's going to be flipped. A lot of different ways you can think about this. Okay, and then we have this possible water oxidation and then this possible reduction. So we have these two choices, or we have these two choices. And again, it's the same rules that we had before. Closer to the top or more positive, that one goes in the forward direction, right? The one that's below it is going to flip or go in the reverse direction and be oxidized. The one on the top, the more positive, that one's going to be reduced. The one on the bottom, the one that's more negative, that one's going to flip and be oxidized. So it's the same rules, but now we have to choose between the two. So the first thing we do is we decide who can be oxidized, who can be reduced. Okay, so remember, let's do reduced first. Reduced, whoever's higher on the table, right? Whoever's higher on the table, whoever's more positive, closer to the top, less negative, right? That's going to be the one that is reduced. So in this case, that will be this one. This one's, we want the one that's higher on the table, the one that's more positive, right? Or less negative. Whichever one you choose. Oxidation is exactly the opposite. For oxidation, right, we want the one that was lower on the table. That's going to be most likely to be oxidized. So the lower on the table, that's this one, right? So lower on the table, you could say it as it's the least positive or the more negative of the two, right? Okay, so remember the reduction. It's the half reaction that's more positive. It's the easiest one to accept the electrons. Oxidation is the one that's more negative or less positive, easier to extract the electrons. So when we do this, we have our oxidation. And so our oxidation, this will be our anode. And this will be our cathode, red cat. This will be our cathode. So when we do this, I think I just have the whole answer for you. So again, now if we wanted to know the amount of voltage it would take to do this, remember this is going to flip. So this will be negative 1.09 plus negative 0.83, right? That's going to be our voltage. And remember, in order to make this occur, we're going to have to add energy in because that's going to be a negative voltage, not spontaneous, right? So we'll have to actually add energy to make this occur. So here's what I did here. So I chose this one as our oxidation. We chose this one as our reduction. And remember, the reduction is just going to be written as is because this is a reduction potential. So see, this one is written exactly as it is. I didn't change it. I flipped this one because I wrote it as an oxidation this time, right? Lose electrons, oxidation. I wrote it as an oxidation. And so again, if you wanted to know the potential, you would have to add this and this. Again, it will be negative, so you have to add whatever is more than that number. Okay, any questions on these? It's the same principle we used before. More positive, more likely to be reduced. More negative, more likely to be oxidized. Right? Just you have to decide the oxidation and reductions and then pick from the two this time. But it's the same principle as we used before. We just have to make one little extra step here because we've got two reactions that we have to choose from. Okay, any questions on these? These are kind of difficult in your brain, so you might have to watch this back again when we're doing it, or make sure you read your book on this very carefully. Until you kind of, it clicks. When it clicks, you're like, oh, okay. You just kind of figure out which way in your brain works better of saying it. Okay, now, stoichiometry of electrolysis is super simple. So what we're going to do in electrolytic cell, again, is the amount of product is made, and it's related to the number of electrons transferred, right? And the electron transferred, you already know that. Remember when we crossed off the number of electrons when we were balancing chemical equations, like we had to multiply them to get 6 on each side? That's the number of electrons transferred, right? So it's, you already know how to do that part. And essentially, like I said, like the electrons are reactants. There's a couple conversions you're going to need to know. First of all, that 1 amp is 1 coulomb, and 1 mole is 96,485 coulombs. And that's called Faraday's constant. You do not need to memorize it. So let's look at how we do stoichiometry. It's very simple. You just have one new piece. Just like a couple extra conversions. So it's a little like reminder of 219 and 209 here, some stoichiometry. So we want grams of AU. That's what we want. That can be plated. So we have 25 minutes, 5.5 amps, and here's our half reaction. And so when we do this, remember, here's what an amp is: 1 coulomb of charge, and 1 mole of electrons is this many coulombs, right? And so our stoichiometric conversions, this is what we have, right? And we want mass. So what we're going to do is we're going to go to amps, then we're going to go to charges, moles, to grams. And again, here's the conversions. Remember, a coulomb, just so you know, 5.5 amps. Remember I said here, 1 coulomb, 1 amp is coulombs per second. So 1 amp equals coulombs per second. So this is that first conversion right here. And again, if you're not sure of the conversion, I think I wrote it. Yeah, 1 amp. So it's 5.5 coulombs equals 1 second. That's what 5 amps mean, because an amp is a coulomb per second. So 1 amp is 1 coulomb per second. So therefore, 5.5 amps, 5.5 amps means 5.5 coulombs per. And if you don't like it, fine, put 1 second. If you don't like it with just a second, right? So that's what amps means. Amps just means coulombs per second. Here's the other conversion I just showed you. 1 mole is 96,485 coulombs. Right, here's this one right here. 1 mole, you can't see it anymore, is this many coulombs. Right, so those are just your 2 new conversions. But otherwise, it's literally just straight stoichiometry, right? And so when you start this, those are your conversions. And so if you haven't had me before in 219 or 209, I will always say this one thing. If you have a choice with units to start with one that has 1 unit or 2 units, start with 1 unit. Minutes is 1 unit. Amps is 2 units, right? Amps is coulombs and seconds. This has 2 units. 2 units. Don't use that one. Use that one. It's 1 unit, right? If you have a choice, sometimes you have no choice, but if you do, choose the one with 1 unit. So when we do this, we're going to start with 25 minutes. And when we look at this, right, this has seconds in it, so we got to go to seconds. So in 1 minute, I'm going to run out of room. 1 minute, there's 60 seconds. And then I can use this, right? So there's 5.5 coulombs in 1 second, minutes, seconds, seconds. And now I've got coulombs. There's my C, that's going to go on the bottom. 96,485 C's, 1 mole on the top. C's. And then remember, the number of electrons, that's the number of electrons, right? If you have a balanced chemical equation, you have to figure out what the number of electrons. It's the number you multiply to get rid of. That's the number of electrons. So in this case, we have, oh, there's my L, sorry. There's 3 moles of electrons for every 1 mole of AU. That's where that mole ratio came from, right? And it's always 1. Well, never mind, it's not always 1, it's usually 1. But that's where the 1 comes from right here. The 3, again, is from here. And then we just use more mass. What is it? It's like 1. Mine says 197. 197 grams of AU in 1 mole.
Wouldn't that be on the top?
Yes, thank you. I should follow my own units here. In 1 mole of AU. That's why we use our units, 197 grams of AU. And I like when you use molar masses, I like you to use 2 places past the decimal, but my periodic table literally doesn't do that on this one. It only has 1. And that's going to be your grams. And so this is like how we do electroplating, right? And so if this is how much AU we could get from electroplating, and you get like 5-ish grams, 5.6 grams. Two sig figs, 2 sig figs, 2 sig figs of AU. So in electroplating, the only thing that's new here is you have this new conversion and this new conversion. And this, remember, this comes from the balanced chemical equation, and this comes from however many electrons you had to multiply to when you added your cells, or if it's straight from a half reaction, it's just the number of electrons in here. Okay, let me, oh, I have it for you. There you are. Same thing, prettier. Minutes, minutes, seconds, seconds, coulombs, coulombs, moles, electrons, moles, electrons, moles, AU, moles, AU. Oh, and I used 2 places on this one, and you get 5.6 grams. Okay, now here's one that we're going to try. It's going to go a little backwards this time. So in this case, we want to calculate our amps. So we want to calculate our amps required, and we're going to start with 2.5 grams in 1 hour. And I gave you 36 seconds. It's whichever one you choose. Okay, all right. So I want you to try this one, and we'll finish it, and we'll go over it in just a minute. Okay. E2 electrons, 96,485. I'm pretty sure. Yeah, 96,485. This is the conversion that you're going to use. So this conversion, and then you're going to find the amps. Okay, so keep working on this one, and then we'll go over it in just a second. So let's try this one. So we have 3 moles again. We have our mass, and this time we are going to end up with C's over S's, right? So we're going to end up with our C's over S's. And, oh, well, I have it all there for you, or it's just going to be green. Okay, so when we do this, again, which one you want to start with grams or time? It'll work out. If you use time, your units will be backwards. And if that happens, it's actually not that bad. All you do is raise your answer to the -1 and it'll flip it all over. So if you started with time, your answer's still okay, right? But you should, in this case, start with grams, because the reason that you can't start with times or time is because your unit on that bottom is coulombs per second. So seconds needs to be on the bottom. So if you start with seconds, it's on the top. You need it on the bottom, right? But again, even if you started with seconds, you can still get the right answer. So if you started with seconds and you got some kind of number, just in your calculator, hit raise to the -1 and it'll flip it over for you and you'll get the right answer. Okay, so if we...
Would it be the same thing to start it as like a per second? So it's like, so just like start it as like 1/3600, and then just like do that same stoichiometry, and then so that way everything is kind of flipped.
Yeah, you can totally do that. Yeah, you can absolutely. That's another way you can do it too. But if you already did your whole problem and you started with 3,600 seconds, you don't need to start the problem over. Just get all the way to your answer and then just raise your answer to the -1 and you'll end up with the right answer. And that works for all stoichiometry. So in this case, I'm just going to start with 2.5 grams because I saw that needed to happen, right? And then our molar mass was 196.97 grams in 1 mole of AU. So moles of AU have to go on the bottom. So 1 mole of AU, and it's 3 moles of electrons. And then we have our, in 1 mole of electrons, 96,485 coulombs, moles, mole. And remember, amps are coulombs per second. So coulombs is on the top. We're all good here. And then, just like Avinash just talked about how he started with seconds. So this is what I do. Some people really hate that though, because nothing's up here. So if you don't like that, oh no, you can just guess your coulombs, which is 3670 coulombs. And then knowing that amps is over seconds, so amps is coulombs over seconds, you could do this, 3670 coulombs over 3,600 seconds. If you don't like the way that I did it, where I just divide in, I'm fine with having an empty box, but some people really hate having that. So this is the way I usually do it. But again, if you don't like it that way, you don't have to do it that way because people hate having nothing up here. I put a 1 if it makes you happy. It's totally incorrect, but that's fine. Put a 1 there. Or I tell my 209 students to put a smiley face. If you really don't like it being empty, put a smiley face there. But no matter what, you're going to get the same answer. In this case, it ends up being 1 amp. How many stick figs? Oh, 1 hour. Did say 1 hour, so it's 1 amp, 1 sig fig. I'm just going to erase this here to make this match. 3670 coulombs. And your answer should be about and around. It should be very close to this. Okay, any questions on this? Question? It's pretty simple. This is 2 new pieces right here. If you got through 219, this is going to be easy for you. Okay, which you all got through 219. All right, so, oh, I have it here nicer for you here. Okay, any questions on this one? Okay, now we're going to talk about corrosion. So we're going to talk about the practical piece of what we've been learning. Not that what we've been doing isn't practical. Electroplating is absolutely practical. But corrosion is the spontaneous oxidation of a metal in an environment. And it's usually due to oxygen, right? And so many of the materials we use are active metals. And so that means that they will often corrode, right? Which means oxidize. So they're going to go from the metal to the ion, which we don't want because we want the metals. And so we use metals because they're malleable, ductile, right? All the properties of metals that we need. So often what happens is the metals will corrode and then a piece will flake off and then the metal below it corrodes and a piece will flake off and a metal below it corrodes and all of a sudden the metal completely disintegrates. Hence, think rust, right? If you ever seen like a rusty fence, that's exactly what happens in a rusty fence. So we're going to kind of look at what happens here. So oxygen is reduced. And oxygen is really easy to reduce in moist conditions, specifically moist conditions here. And if it's under an acidic condition, it's even easier to be reduced. So remember, the more positive it is, the easier it is to be reduced. So if you're in an acidic condition, look at how positive this is for oxygen, right? Super positive, right? And FYI, the water that we have usually that falls is a little bit acidic, right? I think we talked about like acid rain the tiniest bit when we talked about our acids and our bases, right? And it's because the water combines with CO2 and it makes carbonic acid. Which is a little bit acidic. So rainwater itself is a little bit acidic. So therefore, when rainwater, and then if you have acid rain, it's even more acidic, right? And so often it's under these conditions that the water is a little bit of acidic, which creates this acidic conditions. So, but no matter, even if it wasn't, it's still going to be easy to reduce oxygen. And if you look at our reduction table, there's a lot of metals below the 0.4. That's the stable one. There's a lot of metals below 1.23. So here's, for example, I just have this one here for our oxygen. And so you can see all of these metals will be oxidized. Because remember, we're looking at this table. The one that's towards the top is going to go in the forward direction and be reduced. The one below it is going to go backwards in the opposite direction and be oxidized. So all of these metals will be oxidized, right? And so this is why, for example, we talk about iron because we use iron a lot. Our iron will go backwards and be oxidized, right? If we look at this, if we look at the potentials here, when this flips, 0.4 plus 0.4 volts, and this would flip plus 0.45 volts, that's a spontaneous reaction, right? Because it's going to be a positive E cell, right? So this is going to happen. Now, if you look at our reduction potentials, if it was under acidic conditions, that means anything below 1.23 volts is going to oxidize, right? So hence why hence why our metals are always oxidizing. So how do we fix that? So first, let's look at rust just a little bit closer. So we have these two regions. We have this anodic regions and these cathodic regions. So anodic regions are down here. And then you have the cathodic regions right here. So at the anodic regions, you can see that the iron is oxidized to iron 2 plus, right? So it's losing electrons. So it's oxidized going from Fe to Fe2 plus, right? And then you can see that the electrons travel through the metal and then oxygen gets reduced. So here's the oxygen being reduced. In an acidic solution from gases, and so by the way, for this to happen, there has to be moisture. So there has to be some kind of moisture for this to happen. If there's no moisture, then this doesn't happen. But if the moisture is acidic, then we're at the super high potential at 1.23, which is even higher, which is even more. So what happens with this iron 2 plus here? So you've got this iron 2 plus that's mulling around. So here's our iron 2 plus that's hanging around. So it migrates through the moisture to the cathodic region up here. So at the top, it's like our cathodic region. And then it becomes further oxidized to iron 3 plus. And this is rust, right? And this is rust. So this iron 3 oxide is rust. And this is how rust occurs. But again, if you see this, if there's no water, this reaction does not occur, right? And I have the picture again here. The rust, you can see it's a hydrated form right here. It's actually a hydrate. And again, it's got to be, this is all inside a water droplet right away. So without water, this reaction doesn't occur. And so you can see like rust, if you're like in like the Midwest, think of like cars in the Midwest and the East Coast, they rust a lot more than cars that are in like the desert or things like that. Even we can think of it here. People who have cars that are closer to the ocean will rust more than cars that are maybe in like Riverside. Because if you're near any kind of salt like helps us. It's like, remember salt bridge helps the electrons move? Same thing here. So if there's any kind of electrolyte, so salt, like think of like the ocean, the marine layer, or if you salt the roads, if anybody's ever been in like the winter in the mountains up in like in Mammoth or anywhere in the Midwest or East Coast when it snows, they put salt on the roads to melt the salt. You probably learned about that in Chem 219, but that salt is like perfect for the electrons to move, right? It's like a new electron highway. When you've got salt and water, it's even easier for it to happen. So the rusting happens even quicker. So if you have an environment with, we're just saying like a car that you have salt and moisture, you're going to wreck the car a lot faster, right? And that's why if you go through a car wash, they have the undercarriage spray. And what that does is it rinses the salt off, right? So to not rust the engine, or if you get a scratch in your car, well, cars are mostly made of fiberglass, but if you did have metal on the outside of your car, it would rust if you got a scratch. And again, if you have an acid, it's going, if in an acidic condition, it's even going to be greater. So if you have a wet, salty, acidic condition, rusting is going to be rampant. Okay, so now how do you stop corrosion? And so what you can do is you can coat, we're just going to keep using iron. You can coat the iron to slow the corrosion, right? And what we'll do is, I think, let me just look here. I think I have this. I just want to see if I have this on here. No, I only go down to iron. Okay, so I'm just going to go, I have to go to a table to show you this. It's not going to make sense unless I have a table. I'm just going to go back to the first table we've got here. Nope, not big enough. There's our iron. Okay, so what you can do is, here's our iron. So we want this to go in the forward direction. If we want iron to stay reduced, what we can do is we can coat it with a metal down here, right? Because remember, if you pair a reaction, this one will be reduced. This one will go in the forward direction. If you have a reaction that's lower on the table, it will be oxidized. So a lot of times what they'll do is they'll coat it with zinc, or sometimes aluminum. And so what happens if you coat your iron with zinc, your zinc will be oxidized. It will go oxidized. It will be flipped, right? And so if you look here, if your zinc is oxidized, that'll be a +7.6 plus your iron, which is a -0.45. Oh, that's a positive E cell. That's spontaneous, right? Same thing with zinc. Or I did zinc. Same thing with aluminum, right? It'll end up being positive and spontaneous. And so that's what they do. They coat the iron. So the aluminum or the zinc will oxidize and not the iron. The iron will get to stay a solid. And so that's how you can slow or even prevent corrosion. See how fast, sorry if that hurts your eyes that I'm going so fast. Rusting, corrosion. Okay, so again, that's why they use aluminum and they'll coat it with aluminum. And aluminum will oxidize, but when aluminum oxidizes, it oxidizes into Al2O3, which is like a black coating. And it doesn't peel off like iron oxide does. It becomes like a solid surface. So if you've ever seen anything aluminum, it turns like black. That's aluminum oxide, and it almost forms like a seal around the iron. And so then it prevents the iron from rusting. Or another thing that we can do is we can use nails. So nails are iron, but what they cover it with is zinc, right? And again, and we call this like a sacrificial electrode. And again, anything below iron on our reduction table can do this because it will be oxidized. Iron won't be oxidized, right? And so that's why Fe nails or iron nails are coated with zinc, because zinc is easier to oxidize because it's below the table. Now, what about in pipes? So sometimes in pipes, the pipes are made of iron. And so what they'll do is they'll coat the pipe, or actually it's expensive to coat the pipe. They'll actually inject like a sacrificial electrode. And you see this right here, this coating right here. And what this will do is this will corrode first, because it can be, again, anything below iron on the reduction table, like magnesium, aluminum, zinc, anything below it, it will oxidize, which will prevent the rest of the pipe from rusting or oxidizing. And so that's what they call a sacrificial electrode. And you can kind of see how it's like around the pipe right there. And so that's what they do with these sacrificial electrodes to prevent the iron from rusting away. So that is how you prevent corrosion. Okay, so I think that's everything. Yeah.